activities. Today it's a pleasure to continue with first talk by Jeremias Knoblauch.
All right, so I'm going to continue what I talked about on Monday. And so for those of you that weren't here on Monday, I'm sorry if it sounds a bit incoherent. I hope as I continue talking, you'll manage to jump in the boat. But I'm not going to jump directly in. We'll do like a short recap of what we saw on Monday, but it will be quite brief. So those that haven't seen the slides before will probably not understand what's going on. So on Monday, we talked about the assumptions underlying Bayesian inference, and we highlighted that you need to assume your model to be correctly specified. You need to be able to specify a prior on the relevant parameter space, and that prior needs to be well informed in the sense that it should express your best belief about the true state of the world. And we also highlighted that in order for whatever computations whatever posteriors you want to compute to be meaningful, you actually have to be able to compute them in practice. Okay. And so, as we saw, those assumptions were quite fragile in the modern practice of Bayesian inference, which is why I presented this sort of larger space of possible belief updates, of possible posteriors you could compute. And on Monday, I talked about two of these in more detail, namely the cold posterior or power posterior, fractional posterior, and we had like a lot of discussion in the forum as well about their impact in sort of deep learning and how we should interpret them in that setting. And I was starting to talk about Gibbs posteriors or generalized posteriors a bit more. In particular, today, I will continue talking a little bit more about Gibbs posteriors with more of a focus on their computation, right? So we have in principle seen already that we could overcome some conceptual problems with Gibbs posteriors, but last time we ended it on the point that in order to compute them, we need a bit more work because we've introduced this trade-off between computation and robustness now, which is a problem. And the other thing I will talk about today is this further generalization where you just express your posteriors directly as an outcome to an optimization problem. Those of you in attendance of the previous workshop will have seen me talk about this a bit more because I was talking about these predictively oriented posteriors which no longer fit into the framework of Gibbs measures at all, and you have to specify them through this kind of problem. I will quickly touch on them today, but if you want a bigger exposition to them, I talked about them in the previous workshop. Okay, so what we were discussing last time in relation to Gibbs posteriors is, we answered a few questions, namely, why would you do it? And the answer to that was robustness, particularly robustness to model misspecification in the Huber sense. We wondered how you could think about them conceptually, and we saw the classical interpretation of Gibbs posteriors as a general Bayes update. We quickly touched upon Pack Bayes as well as one way of conceptualizing what they mean in terms of generalization bounds. And we saw that more generally speaking, you can view them as a trade-off between a regularization with respect to the prior and a loss function that respects where your data came from. We then asked when they are robust, and I showed you like a fairly straightforward recipe for demonstrating whenever Gibbs measure is robust, and the answer is essentially that they are robust when your loss is. And then we quickly looked at how you could arrive at these robust losses, and we saw that by and large people do so by choosing a divergence and then constructing a loss that approximates that divergence. And we ended on a note of seeing how these divergences sometimes introduce computational problems. Okay, so just quickly, for the kind of robustness we were talking about last time, we were talking about Huber robustness. So if you remember this slide, we were saying, well, most of the data is what I want to model, but there's some contaminants. We saw a talk yesterday that was exploring these kind of contaminations in a more practical setting. Here we're more concerned with the theory, when we essentially want posteriors that perform the same whether or not this contamination is present. And we saw that in a practical sense, Gibbs posteriors can achieve this. So this is how I started the section on Gibbs posteriors last time. We saw there's kind of a Kalman filtering example where these posteriors really enable you to address that kind of robustness elegantly. But then I stopped last time highlighting that some of the early examples of losses people came up with in this literature, so notably the beta and gamma divergences, while they had some advantages, they had the big drawback of not generally being tractable. So in general, these divergences and other divergences as well actually depend on intractable integrals with respect to the model density. And so this now introduces a trade-off between computation on the one hand and robustness on the other. So when you remember the assumptions, we started with assumption 3, which relates to things being computable, seems to be violated in this setting. And so we will turn our attention now to computation for these kind of objects. Okay, so I mean, the first question you need to ask is, what is the sort of simplest thing you can do, and is it a sensible thing to do? Okay, so we know that in some cases, these losses that we want to compute depend on intractable integrals. So the naive thing to do is to sample repeatedly from the underlying model class and approximate the integral as I do up here, right? So we have some kind of function f that depends on theta, and data where that data is sampled from the model itself when it's indexed by theta. We can just approximate this integral in the standard Monte Carlo way. Is this reasonable? No. So here is an example of what happens when you do this kind of procedure inside a standard Markov chain Monte Carlo algorithm to sample from a posterior. So you could think of these approximations the same way you would, if you're familiar with the literature about pseudo-marginal methods. They're essentially doing the same thing. And they suffer the same problem, only it's even worse. So in particular, what you essentially find is that you need to choose the number of samples extremely large to get a reasonable approximation to the posterior you're targeting. So the black line here gives you the exact posterior, and you can see the S is the number of samples you draw through this integral at each Monte Carlo iteration. And that's basically not feasible computationally. Right? So the number of samples you need to draw to make this approximation good is essentially too high. Yeah, so this is the kind of, to be a bit more precise, this is the kind of approximation we make here, right? So instead of computing the loss exactly, because it depends on an intractable likelihood, we just estimate it, where the estimator just replaces the intractable likelihood with a sample. And we do so at each iteration of the algorithm. So you can actually show how bad this is more explicitly. So if we make very favorable assumptions on the loss, this is notably going to be worse if you don't make these assumptions. If we make very favorable assumptions on the loss and the residual error you make when you approximate the loss in this way, and particularly the assumption that I am calling favorable here is a Bernstein condition. So we're assuming we have a kind of Bernstein condition on this residual, which basically means that the loss is something like sub-Gaussian, for example. If this is the case, then we still need to choose the number of samples of order n to ensure that actually the approximated posterior and the exact posterior concentrate at the same rate. And so this is not computationally feasible, essentially, because it means that each MCMC iteration you run scales at n squared. Okay. And so as long as your data is even moderately large, this is not really a feasible recipe. So what you're staring down is the barrel of having to choose between a good approximation or not being able to compute things. So the sort of standard approaches in the literature aren't really feasible for addressing this problem, unfortunately. So what else can we do? We can actually do something that is a bit more modern, and that's quite in vogue, I would say, in the literature on Bayesian computation, and that's, PDMPs. In particular, here we focus on the zigzag sampler. So the zigzag sampler is quite interesting because it only depends on the gradient. And in particular, what we showed in some recent work is that all you need is for the gradient that you're estimating to be unbiased. And so how can we think about this? Okay, so what we need is actually the gradient of L. Now, once again, we don't have that. We only have the gradient with respect to the estimated loss. And for example, you could think under mild regularity conditions, you can hopefully pull in the gradient operator into the way you average. And this is normally feasible. Okay. So for example, if your loss looks like this, and you can pull in the gradient operator like this, which happens to be the case, for example, for the beta divergence I showed you earlier. It's also the case for the maximum mean discrepancy, which suffers this problem as well. You can actually construct these kind of gradient estimators, and then all you need is you need to assume that the gradient estimator that you've constructed in this way is actually unbiased. Okay, so our loss estimate may be biased, and in particular, if you think about what the Gibbs posterior looks like, the exponential of the loss is definitely biased as an estimator. But here we only require the gradient estimator to be unbiased. And if this is the case, we can actually construct a zigzag sampler which has the correct invariant distribution. Why is this interesting? Okay, the underlying math is actually not that hard once you understand the literature on zigzag sampling. The reason it's interesting is that zigzag sampling doesn't really depend on the number of samples at all here. So even with very few draws from the model, we can approximate the underlying distribution pretty much exactly. Sorry, Louis.
Sorry, this might be a stupid question. How can you ignore the dependence of the density on theta when you take the gradient? So you've taken the gradient inside, and it's just applied to the loss.
Yeah. You need some regularity conditions. You need something like Fubini to hold for you to be able to do that. So you can show that this holds basically for these classes of losses. In general, indeed, you cannot ignore that. Yeah. But for the cases of interest, it's actually not a problematic assumption. And so basically what holds here is that you can do this exactly. Just to compare against what we saw before with the MCMC, you can see the number of samples we require are substantially scaled down and the approximations are better. So this is a way of addressing these problems. What's particularly interesting actually for the zigzag sampler, since we've heard a lot about simulation-based inference this week, is so this is actually an example with a maximum mean discrepancy. So you don't actually need a density, you just need to sample. And so if you are in a setting where you may want to do inference on a simulation-based model, you can actually now use these samplers. So there is actually now an MCMC algorithm you can use that does give you fairly reliable inferences as long as you can take the gradient, which you may not. I mean, some simulation-based models do not allow you to differentiate. But if you can, this in principle gives you access to quite a powerful mechanism for doing exact inferences if you care about that. Okay, so this is the second way we can do computation. But actually, I think both of these methods are kind of only interesting in certain model classes. Like you need to be in quite classical statistical settings for these approaches to be scalable and useful. And I think the most interesting case is actually to choose a loss that circumvents all of these problems to begin with. Okay, so here we are going to try and cheat. We're going to try and choose a loss that does all the things we want. It gives us robustness, but it's also tractable in the sense that we hopefully don't have to do MCMC or anything like that. And so when we started looking at this, we were inspired by what people do in intractable likelihoods. So in particular, when people deal with unnormalized likelihoods. So just to recap what that means, an unnormalized likelihood, you have a likelihood function which you have a density for, so this nu here is a density, but it's not a probability density. There is a normalization constant z theta, which you know exists and is finite, but you don't know what it looks like, and it's a function of theta. And in this setting, of course, we kind of have the exact same issue, right? We could just brute force this and draw a number of samples from this density nu, and then approximate the normalization constant, but then we would basically recreate the problems we've just discussed. The other thing we could do is we could try to circumvent the necessity for computing z theta in the first place, and this is something that people do in score matching and its generalizations, such as Stein discrepancies. And whenever you can do this, this is actually really elegant, because not only can you now tackle likelihoods with intractable normalization constants, but actually your entire problem that we discussed, these intractable integrals that are part of the loss function all of a sudden, all of that goes away, because all you really need is a density that is twice differential. Okay, so what do Stein discrepancies, or more specifically score matching in this case, what does this actually look like? So assume we have this intractable likelihood, but you can evaluate the density, okay, but up to a normalization constant. If you take the log of that density and the gradient with respect to the data, you can show that you can essentially just rewrite that as a gradient with respect to the log likelihood itself. And that trick is straightforward. You just divide and multiply with z theta. But the right-hand side object now has a particular role. It's called the Stein score, or the Hivarinian score sometimes. And what you're basically going to try and do is you're going to try and minimize the distance between that score and the score on the data. Okay, that's what happens under the hood in diffusion models, but you can actually use this for parameter estimation as well. Okay, so you can think of this score matching as trying to minimize the distance between the score relative to the data generating density and the model density. And there's some expectations missing in this expression, so it's not mathematically accurate. But basically, what you do is you rewrite this expression. It turns out that you can drop the dependence on the data generating density. Again, there's an expectation missing over x here, otherwise this doesn't work. But once you do this, you end up with a loss that can actually be evaluated on the data itself. And that can be evaluated even if you don't have access to the normalization constant. Okay, so score matching actually corresponds to the Fisher divergence, which is nice. And so once again, we have this duality where a loss corresponds to a particular divergence, which is nice. Now remember, on Monday, I talked about how we wanted to abandon the log score because the Kullback-Leibel divergence, which is the divergence that it corresponds to, is not robust. And actually, we have a problem here because the Fisher divergence equally is not a robust divergence, which means that score matching is not actually a robust loss. So, okay, so we've made it tractable, but now it's not robust anymore. Fortunately, that problem is quite easy to solve. All we really need to do is we need to suitably modify the Fisher divergence and expand our horizon into a larger class of divergences that encompasses the Fisher divergence, and that's the Stein discrepancies. So Stein discrepancies will allow us to derive losses that are robust, but that, like the score matching loss, actually only depend on the Hivarinen or Stein score of the model. And so that's what we're going to do. So apologies for those of you who work on Stein discrepancies, because I think the level of accuracy on this slide will be insulting to you, because it's quite a deep mathematical topic. This is just to give an overview of how we construct these Stein discrepancies. So Stein discrepancies are a modification, essentially, of an integral probability metric, which is self-referential. What I mean by that is that in the case of a, do I have a pointer? No. Okay. In the case of a integral probability metric, you would take the supremum over a function class that doesn't depend on theta. In the Stein discrepancy case, you change this. The supremum itself now depends on theta, i.e. depends on one of the arguments with which you want to compute the distance with respect to. And what you're looking at is essentially the worst case between two measures that you're integrating over a class of so-called witness functions, except the class of witness functions depends on one of the things you're comparing. Why do you have this weird dependence on theta in f? The reason is for this that you want to eliminate one of the expectations. Complicated enough to compare the supremum between two expectations. So what we're doing here is we're eliminating one of them by choosing this function class so that one of the expectations is always 0. And actually, this function class will be chosen in a way where it depends only on the Stein score, where it depends on the model only via the Stein score. Okay. So the other thing you do is you make sure that, because it's also difficult to compute the supremum over one expectation, you make sure that actually, in essence, you have a kind of closed form solution f star, which lies in this theta star, in this f theta space. And you achieve this essentially by choosing a smart combination between what's called the Stein operator and the Stein set. I'm not going to go into the technical details. Again, those of you who work on Stein discrepancies will know what I'm talking about. But essentially, you carefully design this supremum problem so that you end up with something computable on the right-hand side. And then, because you've chosen everything so that you essentially end up with a singular expectation over Q epsilon, and you have samples from your Q epsilon, it's now actually simple to approximate this into some loss function. And here an important detail that I've mentioned already is that essentially the dependence on the model only comes through the Stein score, but additionally, and that's the difference to vanilla score matching, additionally, we have this weight function W here, and that weight function W ensures that things are robust. Okay. So W responsible for robustness, and the log score responsible for the fact that we can actually evaluate things. And so we end up with a loss that's tractable and is robust. And it doesn't need sampling. There isn't any intractable integral left here. Okay. So it's useful to compare what these losses actually do once we plug them into the Gibbs posterior. So we already said that they're robust. I'm not going to explain why or how this happens, but essentially these weight functions W, what they do is they downweight data points that are increasingly less plausible. Okay, so they essentially have an effect that is very similar to what you would do in Huber losses. So you downweight the influence of data points that are unlikely on the Stein score. Okay, so we have robustness in the Gibbs posterior when we plug in these losses, which we know we don't have for the base posterior. How about computation? If we start with an intractable likelihood, then actually these Gibbs posteriors are now much faster to compute than the base posteriors because we don't have to deal with the doubly intractable problem. Okay, so the likelihood normalizer is irrelevant for the computation of the Gibbs posterior. It still matters for the base posterior. If the model is tractable, basically both are roughly as fast as one another because you use the same kind of techniques, the same Markov chain Monte Carlo methods for both, or your variation approximation, whatever you want to use applies to both. They basically be as fast. So the one case where you would think that, at least in terms of the computation time, the base posterior is preferable is the conjugate case, where you start with an exponential family model and a conjugate prior. Right? Because we know that in that case, the base posterior actually has a closed form. So it would be reasonable to assume that that luxury is not present for Stein discrepancy-based Gibbs posteriors. But actually, you'd be wrong to assume that, because what happens to be the case is that the Stein discrepancy posteriors do lead to closed form posteriors, or can lead to closed form posteriors whenever A, you have an exponential family likelihood, and B, you choose a essentially Gaussian-like prior on them, and then you have everything in a conjugate form, not necessarily closed form, but always conjugate. Okay, let me explain a bit. So, if our parametric family belongs to the exponential family, possibly with an intractable normalization constant. So this applies even in a setting where you don't know the normalization constant of the exponential family, as for example in graphical models. In any such case, this loss looks like what I've drawn on the right-hand side here. And that, if you look at it, is just a quadratic form in theta. Now, what we care about in the end is, of course, the negative loss exponentiated. And the negative loss exponentiated of something that is quadratic is essentially like a Gaussian. So you're starting with this discrepancy, and you end up with something that looks a lot like a Gaussian likelihood. It's not a likelihood function, right? But it behaves in the same way as a Gaussian likelihood function in theta, in the sense that once I put a Gaussian prior on it, or more specifically a squared exponential prior, I end up with something that retains the same form. So it remains a squared exponential posterior. Why do I call this a squared exponential and not a normal? The reason for this is that the theta here may not live in the entire real line. So if your theta lives on the entire real line, this is just a normal, has closed form, we're all happy. But you could imagine a case where the theta is only on the positive reals. This entire conjugacy property still holds, except now you have a truncated Gaussian prior and you have a truncated Gaussian posterior. Okay. But it's still conjugate. And that's why there's a slight differentiation between saying it's available in closed form and it's conjugate. It's always conjugate, and in most cases where your theta is defined on the entire real line, it's also closed form because it's a Gaussian. Okay, so we have a closed form, and notably we have a closed form even if the original likelihood we started with was actually intractable. So imagine you construct a likelihood in a sort of graphical model where you have some kind of intractable likelihood, which is very common, and specifically which is very common, and you run this method, you essentially don't have to deal with any of the nastiness that you would normally encounter in the Bayesian case. So this can give you access to posteriors that are available in closed form in situations where the base posterior is what we call doubly intractable, which means you don't know the normalization constant of the base posterior, and you also don't know the normalization constant of the likelihood. So actually, there isn't a problem here. You are as good in computation as the base posterior, and sometimes better, particularly if the likelihoods are intractable, even for exponential families. And so obviously, we were very excited about this finding. So we have like a number of papers where we've exploited this property. Most recently, we started exploring this property in the context of Gaussian processes. So we have a paper this year at ICML looking at this for spatiotemporal Gaussian processes. We had a spotlight last year, sort of laying the groundwork for that. And we have some upcoming work where we look at deploying this kind of logic for active learning. So which is more relevant, I think, for the experimental design feature of this workshop. But we're starting with baby steps. So we're not having like any massive applications yet. It's mostly doing the basic theory. But I'm hoping that this kind of logic can ultimately give us Gibbs posteriors that are practically meaningful for large-scale applications, specifically with Gaussian processes. And just to give you an example of some of the recent work we did, so if you fit a Gaussian process with outliers, so let's say you observe temperatures across Europe and you fit a vanilla GP to it. I've injected some outliers where it's really warm in England in November. So, I mean, you're here in summer, you don't get to experience this, but it's not that nice normally in November, okay? So you inject some outliers, and here you can see the in-sample fit of the Gaussian process. So obviously it's going to fit to the outliers, but the really alarming thing is what happens out of sample, okay? So if we're trying to predict the weather for December, we definitely don't have White Christmas this year because the GP is essentially overfitting to the outliers in the previous month. If you compare what happens with a robust GP in this case, is you essentially get the same results for both September and October, And then once you get these really implausible values that tell you that it should be really warm around London, and even though they're clustered spatially, essentially you can see that even in sample they are being ignored. And then if you pose a prediction in the next month, you also ignore them. Okay. Right. Okay, so that brings us to the end of the Gibbs posterior chapter. So I already recapped most of this, but just to recap what we covered today, which was mostly about the computation, we saw three different approaches. The first of them is kind of the naively plugging in an approximation of the loss that's based on samples and seeing how that actually fails, like a pseudo marginal approach. It's not necessarily good because you need to sample so many times from the model to make this work that it's essentially not worth it. The second approach we looked at is zigzag sampling, which was more elegant in the sense that the approximation quality didn't depend on the number of times you sampled from the model. And then the third approach that I'm a strong advocate for is choosing the loss in the first place so that there is no intractable likelihood, i.e. Cheating. Okay, but one big drawback of all of this, right, is we were singularly focused on this kind of Huber contamination and inference with outliers, trying to avoid the influence of outliers, which is quite limited, right? But it doesn't really tell us anything about some of the other problems we highlighted at the beginning of the talk yesterday and also today, which is that your prior might be poorly specified. And in machine learning, you may actually not care about parameter uncertainty at all. You may care much more about prediction. And so that's what I'm going to talk about in the last 20 minutes or so, which relates to this third instantiation of the sort of post-Bayesian landscape. Before I do that, if people have questions about the Gibbs posterior chapter, now would be like a good moment to ask them.
A quick one about the exponential family case when the params are not all on the real line. Like the standard score matching loss there wouldn't be applicable in a sense because of the
because of the boundary problems.
Problems. I mean, a simple fix is to just consider the log parameters instead. Is that what you're doing, or why? In other words, if the parameters are not on the real line, what do you still get a closed form solution?
So you get a conjugate solution. It need not be closed form. The boundary problem you can avoid with this weight function. So one of the effects this weight function has relates to this as well. So we introduce it for robustness, but actually one of the side effects is that you can now differentiate at the boundary.
That's the difference between the standard score matching loss and the Stein.
Yes, this is one of the differences is in that way. Yeah. Yeah.
And follow up maybe. Does it also work for discrete feedbacks?
So we're working on that now. So obviously not immediately because you don't have gradients. But so what we're working on at the moment, so we have some prior work on this at JASA actually, but I don't love that work because it doesn't really give you the computational benefits. For me, the main reason of doing this is that you simplify the computation. That work doesn't give you that, but I will forward you the work once we do it. Essentially what you do is you define a kind of pseudo derivative operator on a spatial arrangement, which you do via neighborhoods. So you kind of pretend like neighborhoods that are close to one another in a spatial sense behave as though they were a gradient.
Some ordering.
Yeah, you need some ordering or some graphical structure really on what kind of observations are close in the discrete space, which is normally not too difficult to do. The ordering is mostly in a 1D sense, but you could imagine that you have like a spatial lattice, or it's 3D, or it's KD, and then you need to think more in terms of neighborhoods. But yeah, you can do this. We're working on this now. Okay, I shall continue. Right, okay. So with this last part of the talk, I want to answer three main questions. So these are very open questions for the large part. So there are not good answers available to them. So what I showed you for the Gibbs posterior is, I think, it's very mature research in the sense that the mathematics has caught up with our intuitions to some extent. There's still a lot of work left to do, as we were discussing on Monday as well. The sort of fine-grainedness of our robustness assessments needs some work. But by and large, it's quite a mature field now. This is not. So a lot of the work here is fairly trying to figure out the direction of the wind. And so one of the questions we want to ask is how we can get robustness to the priors and how we should think about this in light of these optimization-centric posteriors. Another one, and again, this is what I mentioned earlier, is how we can use this to improve the posterior predictive or the predictive. And so Like I said, I gave a talk at the other workshop where I was giving more of an overview of that question. So if that's something that interests you, I think the talks were made available recently to watch online. And then lastly, and this is quite an interesting question for the people here that work on stuff like Wasserstein gradient flows, is how do you actually go about computing these objects? Because these are not available in any analytic form. They are only specified as the outcome to an optimization problem. So you do need to think about them as though you do some kind of gradient descent on the space of measures, which directly leads you to Wasserstein gradient flows. Okay, so just to motivate very quickly why we care about these optimization-centric formulations. So when you write down the Gibbs posterior, one way of writing it down that we saw on Monday as well, is you can think of it as the trade-off between a loss that tells you how good the data is described by a given parameter, and a regularizer that tells you how far you're deviating from your prior beliefs. And you can essentially generalize this in three ways. So one of the main ways you can do this is you can deviate from the loss. So we've explored many losses in this talk already. All of them, though, were expected losses in the sense that they were linear in Q. Okay, so far, the only kind of loss we've explored had the form above. You could think of losses that are no longer linear in Q. There's some weird other function of Q, okay, in order to maybe obtain some other form of robustness or better predictions. Likewise, you can think of the regularization as being, it's sort of arbitrary to regularize with respect to the Kullback-Leibler divergence once you deviate from base rule anyways. And there's no real reason to stick to that anymore. And you could, in some situations where it's warranted, change the divergence to be more robust to, for example, poorly specified priors. So this is something that's relevant in the deep learning literature, actually. And then lastly, the other thing, and it's the least interesting because I think people are well aware of this, is you can just change the set over which you minimize these problems to be, for example, parametrically constrained, right? In which case you do variational inference, or you can choose the set of measures that are finite second moments, in which case this is very immediately something that corresponds to the Wasserstein gradient flow. Okay, so let's discuss what you can do if your prior is bad, in the sense that it's way off and it's at best the best guess. Once again, I think the right setting to set the scene for this is Bayesian neural networks, where your prior definitely doesn't express what you want it to express in a sort of orthodox Bayesian sense. Right? This is not your best rational belief. You haven't consulted a million experts to tell you what the 64th weight in the third layer should be. Okay, this is like a best guess at best. What can we do with this, if anything? One thing we can do is adjust this regularizer, right? So we want the prior regularizer to be more forgiving for bad posteriors. We don't want to be constrained to something that we know is bad if the data tells us that we should escape it. And so you can actually view this in a way that I think is quite informative, what this regularizer does, and that's by looking at the Lagrangian. Okay, so we're looking at, looking at this as the Lagrangian. So you can actually rewrite this entire problem as saying we're trying to minimize some kind of loss on Q subject to being in a delta ball around the prior. And that tells you the influence of this divergence. This divergence tells you which space you're allowed to search over when you're looking for the posterior. Okay. So if you change this divergence, you're changing the geometry of the ball, and therefore you're changing the nature of the optimum of this problem. And so that's quite relevant for Bayesian deep learning because the shape around this prior determines the robustness, and our priors are rubbish in deep learning. So we want to be able to escape in certain directions, but maybe not in others. So we know, for example, that we don't want the posterior to be having too much variance in Bayesian deep learning. That's like known to be a bad thing. And so you may want to choose a ball that dissuades you from doing that, but incentivizes some other behaviors. To give you an example of how this manifests, so this is some work that wasn't actually done by me, but it was done by Veit Wild, who's unfortunately escaped to industry. But so Veit asked this question, essentially. He was looking at standard Bayesian computation. So actually here, you're even doing exact Bayesian computation. So there's no approximation. Okay? So you have a Bayesian neural network here, and what you can see in the top is essentially predictions. So this is all on the data space already. You can kind of ignore it, I think. Just follow the line that's drawn across, which we've projected down here, And you see these light blue bands as sort of the uncertainties around your predictions. Now what you can see is that essentially you immediately mode collapse, which is kind of a well-known behavior of the KL. Okay? And what I mean by that is where you observe data points, so where you have these red clusters, your predicted uncertainty is completely collapsed. There's nothing. And then even in between where these clusters are, there's barely any uncertainty left. Okay? So it's a fairly overconfident model that you've fitted there. And actually, once you start doing stuff that people do in the real world, like approximating the base posterior, this gets much worse. So whether you use a mean field variational inference method or, let's say, dropout, the problem gets worse. Okay, your uncertainty collapses even more around where you've observed the data. And this is fundamentally related to the way that the prior feeds forward here. But I want to highlight one thing, and that's that the approximation here worsens the problem, but the problem was present in the exact version as well. I mean, this may look better than this, but this is really not great, right? I mean, your uncertainty around where the data is completely collapsed. There's no uncertainty left here in your parameter estimates. And so one thing you can do, and we don't really understand exactly why this works or how this works, but you can change the way you regularize the data. And actually then the degree of your uncertainty quantification changes quite drastically. So, okay, you still collapse around the data points, but your uncertainty as fed forward into the prediction space actually looks very different qualitatively, and arguably is a more honest assessment of the uncertainty you have. Again, there's no theory attached to this yet. We don't exactly understand how this works or why this works and which regularizers give you a better degree of uncertainty quantification, but what we do know is that the impact of the regularizer is substantive if your prior specified data.
What's the better uncertainty?
Sorry?
What's the better uncertainty?
Yeah, I don't know. Like, I think even that question is unclear. So this is a purely qualitative inspection, right? But I think you would probably agree that this is not good uncertainty. No? I'll give you a sheet of paper later and you can sign saying that you think this is good.
No, you know where I'm going.
No, I know exactly where you're going. We don't have
scoring.
100%. 100%. So this is why I'm saying like this is very undeveloped because the exact mathematical grammar to make these statements I don't think exists yet. Right, okay, so I just wanted to show this, and I share all your concerns, like what am I even saying here when I say it's better uncertainty? I think it's a very valid point, yeah. So let's change to something where we have developed the math, and what I talked about last time, which is if we have bad predictives, what can we do? And actually it turns out the answer to that is pretty straightforward. You can just change the way you score your model, or you score your posterior, into scoring the predictive implied by your posterior directly. So again, when we start with a normal, go away, Board of Examiners, boo.
Where's it cross?
I can't find my mouse somehow. It's fine, okay. You'll manage. Let me just do this. Right. Okay, so when we build these Gibbs posteriors, classically we build them based on scoring rules. So scoring rules correspond to a discrepancy. I was framing everything in terms of discrepancies, but often the most amenable discrepancies for parameter estimation are actually ones that are based on scoring rules, which I'm denoting by S here. So scoring rule tells you how good a given model describes a data point you've observed, and once you average over the data generating process of the second argument, you actually end up with a score between two measures, which once you subtract the expectation of the score with respect to itself, you obtain the corresponding discrepancy. Okay, so this is how we typically construct these Gibbs posteriors. And the base posterior is an example of this, where the scoring rule is now the log scoring rule. And what's interesting here is, okay, so now I'm replacing all these losses with scoring rules. But what's interesting here is that all of these scoring rules actually still try to fit a parameter. Okay, so all of these, okay, I don't have that slide here. All of these scoring rules, they are still geared towards finding the best parameter in your parameter space to describe how the data were generated. But if we care about the predictive, that's actually not what we want anymore. We want to find the best predictive, which is a fundamentally different problem. And to sort of showcase this problem, so let's assume we have a base posterior here. If you have some kind of training data that you fit to your posterior, so we have these little triangles and these little circles. This is our in-sample training data, so we fit that to the base posterior, in this case in the log-Kerbel-Terra model, and then we try to predict on the out-of-sample component of what we observe. And so forgive me for these very small lines, but you see these very small gray lines? That's the truth. And you see these blue lines and the red lines, that's where we predict that the data should occur. And as you can see, there's no overlap whatsoever. And more alarmingly, there's actually no uncertainty around our predictions either. So you see here in the legend, there's this sort of gray area for where the predictive should be. You don't see any of that in the out-of-sample component. And the reason for that is that the base posterior has basically fully concentrated around a singular parameter value. So all your predictions revolve around that one parameter value, and you essentially don't get any uncertainty back. So your predictive here is extremely poor. You get the same problem actually for any kind of score-based model. So for example, if you run a Gibbs posterior with the maximum mean discrepancy, you have the same problem. And so notice that the problem here is not a lack of robustness, because the MMD posterior is actually robust to model misspecification. The problem is that the robustness is not meaningful, because what you want is actually prediction. So the robustness is expressed in terms of how close you are to the best possible parameter, okay? That's not what matters here. What matters here is the predictive. And so the reason this happens for the Gibbs posterior as well as for the base posterior is that the Gibbs posterior concentrates normally to essentially the empirical risk minimizer, and it does so normally at rate square root n. And as a consequence of this, the predictive that it implies also concentrates, essentially to plug-in predictive. And so we have some formal results where we show this. And this means that, whether you take a power posterior or a Gibbs posterior, if you care about prediction, eventually it doesn't help if your model is misspecified. And so, so as I said, this is because the Gibbs posterior itself collapses around a point mass. And it makes sense that it does that. If you actually care about parameter inference, as you get more and more data, you want to collapse around what you believe to be the best possible parameter value as you get more evidence of that parameter value being good. But that's not what we want when we care about prediction. So we need more, and we need to, in particular, avoid the collapse of the Gibbs measure around a point mass. And so what you could do instead, right, so we saw in these Gibbs posteriors, we target a score that assesses how good a given parameter value is. What we could do instead is repurpose the score so that it targets the best predictive directly. So what that means is you're now scoring the implied predictive distribution with the same scoring rule. And if you do this, you end up with something that you could call a prediction-centric posterior or predictively oriented posterior. And this targets the predictive directly, and it won't collapse. Okay, so we have some upcoming work on this, and I'm not going to go into more detail because I covered that in the last workshop. But what I will sort of briefly show you is that now you actually get meaningful uncertainties around where your data occurs and also where your predictions occur. More importantly, I want to focus on computation. So I can write down this Qn, but it doesn't have analytic form, and this raises the question of how I should go about computing this object. And so essentially what you can show, what we have in some forthcoming work, which we will show, is that these scores can actually be rewritten as a linear object over the product measure. Okay, so there's essentially a representation of these scores very often. And we've already exploited this, so if you've read the paper that we wrote on doing this with maximum mean discrepancies, there, this link is exact. You can rewrite the score between the predictive and the data as a linear function relative to the product measure Q for some K. So you take the Q to a K product, and suddenly everything is linear. And this is really nice, because now you have essentially a linear function plus a convex regularizer. And this is amenable to two forms of analysis. The first of these I'll skip. But the second is relevant here, which is essentially a gradient-based approach. So once you write this all out, you end up with something that is, if you want, k-linear in Q. Okay, so it's a product, so it's k-linear. And it's strictly convex. And in fact, the way I've written it here, you can see that once you think about the product measure itself, it's actually just linear in the product measure and convex in the product measure. And that's because of how we've rewritten the KL divergence here. Right? So we've just rewritten the Q as the product measure Q and then divided by 1 over K, which you can do for the KL. Okay. And so this representation is really nice, A, for theory, because this allows you to tap into backpack Bayesian analysis. But B, and that's more important here, for gradient descent, or Wasserstein gradient flow. So the Wasserstein gradient flow gives us a way of essentially implementing a gradient descent scheme on a space of measures for these predictively oriented objects. And so, yeah.
Jeremias, how constraining it is to assume this product?
It's not constraining. So this is actually exact for example, the maximum mean discrepancy, the CRPS, you have this exact form, so it's just a representation. For something like the log score, you have an arbitrarily good approximation. So in general, for convex scores, you have an arbitrarily good approximation. So, okay, so what you want is p theta dq, right? So let's write that with respect to a singular point like this. So that's really what you want. If you use Jensen's inequality, you can, and the score is convex, you can upper bound this for any k with, so how's this work again? Oh, sorry, no, that's right, okay. So we have the expectation over theta 1 through k sampled from qk over s. Yes, so this should be summing here. 1 over k j s theta j xi. Okay, sorry. Can you see this? So you can do this for any k, and actually you can show that as k goes to infinity, this inequality becomes an equality. And so we have some preliminary results where we show that these things actually, under mild regularity conditions, they're quite arcane. They come from the sort of important sampling literature for variational inference. But essentially what you can show is that as k goes to infinity under mild regularity conditions, the right-hand side and the left-hand side become uniformly close. And so this approximation actually is very powerful. It's very good. So in this case, this is now what I've written as this S function here. And so in this case, it's approximate. But in general, for several scores, this is actually an exact representation. Okay, I've got like 10 minutes left, so I'll speed up through things. Okay, so basically the way you can sample from this, and this is quite underdeveloped, but the way you can sample from this is, via kind of SDE that you evolve, which symmetrizes and takes the gradient of this function S, which was the linear function, and then you have your kind of prior regularizer having an impact as well, and you have a Brownian motion giving you the sort of movement through space. We haven't analyzed this properly yet, but this definitely works, and we have analyzed it in some specific subcases, but not in a good enough way. And actually, so one of the reasons why the analysis is hard is that you now have interacting particles. So unlike standard sampling algorithms, now your algorithm depends on multiple particles, and you have to push the number of particles to a large number as well, because the measure depends on them interacting. So it's kind of the same problem you have with SMC algorithms, where you need to consider these joint limits as the number of particles and the time horizon goes to infinity. Okay, anyway, so to wrap up this part, we asked, how can we get robustness to the regularizer, and we saw that you can possibly do that by adjusting how can we get robustness to priors, and we saw that we get something from adjusting the regularizer, even though it was queried whether that was good uncertainty, which is it's a very fair query. And there's very little work done on doing this properly. We also asked whether we can use this kind of representation to improve the predictive, and I rushed over those results, but the answer to that is definitely yes, and there's more to come in this space. And then I quickly gave you some overview of how you could hope to compute this in the most general way. And I jumped over the projection case, but I focused on how you could do this with Wasserstein gradient flows, or a form of gradient descent. Okay, so there's lots of new technical fronts opening up, and I could give you like a long list of open questions, but I don't think I really want to end today in that way. So instead, I kind of want to zoom out a bit and ask again the question that we started the talk with, and that's why do we actually need this kind of post-Bayesian rethink of some of the methods that we've been working on? And I think it's most obvious in the context of machine learning. So for example, let's assume we actually run the Wasserstein gradient flow on an objective that looks like this. Okay, so this is an objective that corresponds to the cold posterior or the base posterior. If you do this, you end up with a Langevin diffusion, which we all understand. It's nice, it's sort of classical stats. it converges to a well-defined density, and it's a very well-studied algorithm. Everybody's happy. What happens if you push the lambda to infinity? Actually, it turns out you end up with something that's very popular in machine learning, which is the deep ensemble. So this converges as well, but it converges to a kind of ill-defined discrete measure. When I say ill-defined, what I mean is that what this converges to depends entirely on where you initialize, because all these minima are local, and this is a deterministic process. Okay. So these two algorithms actually don't have very much in common in practice, right? One of them is kind of well understood, it's a density. The other one depends entirely on where you initialize, which also the Langevin algorithm, I should say, doesn't depend on. And so you would think, looking at them, that actually they solve completely different problems. And so this is a problem because in the machine learning literature, you will often find the claim that deep ensembles implement a version of Bayesian inference. And clearly, in a strict sense, this is not true. If you look at the previous slides and if you do the analysis properly, they're not the same thing. I mean, a base posterior and a deep ensemble, they have fundamental differences. But in a moral sense, I think there are some similarities with what both approaches attempt to do. And so, for example, this is one paper that Andrew, I don't know if Andrew's here today, but Andrew was involved in this paper, where they make the argument that actually you can think of deep ensembles as a way of implementing a kind of Bayesian inference in deep learning. But they do use the words like Bayesian inference in a sort of orthodox way. And that's perhaps confusing because clearly deep ensembles are not doing orthodox Bayesian inference. And so my sort of conclusion for today will be that I think, whether you like it or not, sort of orthodox Bayesian uncertainty quantification in machine learning is kind of a lost cause. I think in many parts of Bayesian, in many parts of machine learning, that has already been long abandoned. And we have no hope of recovering some kind of lost past. Okay? We should not go venturing for Atlantis. If for example, these deep ensembles, they don't even use a prior. There's no prior regularizer there. It's a discrete measure. A base posterior is a well-understood object. It depends on the prior. It has densities, yada, yada. These are completely different worlds. And I'm not saying one of these worlds shouldn't exist. I'm saying they are very different desires that we're trying to encode. But as a field, I think statisticians in particular haven't really paid enough attention to the ramifications of this. And so we haven't really engaged with machine learning in a constructive sense. I mean, you will often talk to statisticians who will just basically say, oh, they're doing it wrong. And it's like, maybe, but they're doing it wrong according to the principles we've outlined for a different problem. And so I think it's our job as sort of technically oriented ML people or statisticians to come up with good and new formalisms that actually help people in machine learning come up with something that hopefully is a bit better developed and a bit more, principled rather than just the first random thing they could think of and maybe it works. And so if we do this, then I have the hope that we could prevent people from making claims that are perhaps reaching a bit far or incorrect, and we can help people steer ideas in better directions. And so that's where I want to end today, on this hopeful note, that I think there is a role for us in the future, and I think diffusion models are a good example of where I think this has happened already, and where there's a very fruitful exchange between the statistical and the machine learning community. And I think as Bayesians, and people interested in Bayesian experimental design, maybe we can learn from that and contribute to that front as well. Okay, I think I have about 5 minutes left, so I'll just take questions if you have any left.
Here we have time for questions.
Thank you. That was nice. Your temperature example. I completely agree with the sentiment. I don't like the particular example because the outliers in temperature are usually the most important.
Sorry, say again, the outliers?
So usually when you're modeling temperature, it's the outliers that matter.
Yeah.
Right? So in this particular example, if you left out November and then you tried to predict November, given September, October, December, could you do that?
Sorry, in this example, if I left out November, okay, so I don't observe any data for November?
Yeah, so because here you try to predict December,
Yeah.
you could also leave out November and predict that,
Yeah.
right?
So I think in this example, there's actually like 2 or 3 years of data before that as well. So you could predict it, yeah, and it would probably do something reasonable. But I haven't checked. I don't know. I mean, fundamentally, I agree with your point. Like, this is not a good example. It's just data that was available. So this paper didn't focus on temperature modeling. I agree that it would be egregious if we did. Yeah.
Yeah, so I'm coming from geophysics or earth sciences in general, and I think what you say, I mean what you present, but also what you say with respect to the deep learning community, I think it also applies to the earth science modeling type of community. We have likelihoods that are not typically well defined, but we also have priors that are well defined, and we still want to estimate uncertainty. And I think many of the approaches we actually used in the past actually look quite a lot like the approaches that you now present in a more, let's say, formal way.
Interesting.
While I guess I've been going the other way. I've been going from that type of approaches to a Bayesian approach and realizing that, yeah, you have all those issues. So I mean, it's very interesting, and I just want to say that I think for the whole earth science, climate type of community, I think there's a tremendous literature by one person called Keith Bevan that has done something called glue, which is very much related to this thing about how do you deal with the fact that you can't define a likelihood, you still want to do a certain qualification, your prior span and so on. And he has invented his own terminology for this, but just saying that there's been a lot of discussions since ages also in that community.
That's really interesting. We should chat about that more. I would like to learn more about that if you can. I didn't quite catch the name, so I'll come up to you later because that would be really interesting, I think. Thank you.
So in the paper by Vasily Holmes and Walker, they make this argument that if you want your posterior update rule to be coherent, then the KL is the only choice for regularizing the theta, just to the right.
Yeah.
And so, is there like some benefit to giving up? Because to me, reading the paper, it feels like not wanting to break coherence is why they didn't try a different regularization. They only considered different losses.
Yeah. So I am. I'm not convinced of that argument. So it's true technically. So if you define coherence the way they do, then this is true. I think the main reason for choosing, so just for those that may not spend every second day looking at that paper, coherence is basically the idea that if I have a posterior based on n-1 data points, based on x1 and -1, and even if this is some kind of Gibbs posterior, I can update this. That's essentially the payoff you get. Sorry, let me, it's n. You can update this with essentially what is a pseudo likelihood, where now, so you have an individual loss, and we have assumed that this loss is summable. Okay. So the payoff of the coherence framework is you can do this, right? You can do these recursive updates. So the entire point of Vasily Holmes and Walker is the paper is called general belief updates. So they want to do a belief update. And I think if you want to think about these things as consecutive sequential belief updates, you definitely need this. And then you need the KL. So if you want to be able to write things in this way, I agree. In practice, I think it's a bit of a distraction because for example, whenever you compute a variational posterior, that's no longer coherent, right? So even if the underlying base posterior was coherent, once you approximate that thing, no longer coherent. You may be interested in some losses that just aren't summable. So specifically, if you look at data that, when you are actually worried about outliers, one of the most useful things you can do is let the data speak to one another. So for example, some of these Stein discrepancies actually look like U statistics or V statistics. And the reason this matters is that one point is compared with all the other points. And that's actually really informative if you want to know whether one of them is an outlier. So there's some limitations that you run into when the loss is summable. Certain things you cannot do when the loss is summable. Whenever your loss is summable, and you can afford the computations to make these things sequentially amenable in this form, I think it's nice to do this. Certainly computationally, this is really attractive. But for me, the coherence argument is, it's mostly, the way I read it is mostly as a computational convenience argument. I don't think there's like any deep conceptual reason for doing this, personally. Once you give up the base posterior, even if you do something that looks a bit like the base posterior, it's not. And in fact, we can talk about this a bit more because I think I'm running out of time, but we can talk about this a bit more in the break. There's like a number of reasons why I think this perspective is somewhat limiting. But indeed, for computational reasons, I agree with this completely. If you have a loss that's sum of all, and you can actually compute things in this update form, there are several advantages that should lead you to this as being the first thing you check whether it makes sense.
Thank you again.
Thank you.